So we can express current in terms of drift velocity of the moving charges. Let's consider again the same situation here. This is a conductor with some cross-sectional area A, and electric field is directed from left hand side to right hand side. So let's assume the free charges in the conductor are positive. Okay, and if they are positive, the drift velocity is in the same field as the is in the same direction as the electric field. Now let's suppose that there are n charged particles moving per unit volume. So these n charged particles uh, are the concentration of the particles, and all these particles are moving with the same drift velocity of magnitude vt. In some time interval dt, each particle covers a distance vd into dt. The particles that flow out of the right hand side, this side of the cylinder, with length vd into dt during time interval dt, are the particles that were here within this cylinder at the beginning of the time interval here. So the volume of the cylinder becomes A V A Vd into dt, AD AD, and which is equal to this. So volume becomes A Vd into dt. This is equal to the distance d, and the number of particles within this are n A Vd to dt. Now if each particle has charge q, then the charge that flows out of the end of the cylinder, so if each particle has charge q, the charge dq that flows out, okay, from this cylinder during this time interval dt is q, and this charge becomes n q vd into A into dt. We know that current is current through the cross-sectional area A is equal to the net charge flowing through the area per unit time. I is equal to dq over dt, in other words. So I is equal to, and just put this value, and the current becomes nq vd into A. The current per unit cross section area is called as current density, which is denoted by J. We can write J is equal to I over A is equal to NQ to VD. If the charges are negative, if the charges are negative instead of positive, then the drift velocity is opposite to E in this direction. If the charges are negative, then but the current is still the same in the direction of E at each point in the conductor. So the current I and the current density J don't depend on the sign of the charge. So in this equation, we will take the absolute value of Q. So this become N Q into Vd. Because this is, we can also define current density as a vector current density. So this equation becomes NQ into Vd. This is vector current density. Now, if the conductor may in conductor sometimes there are several different kind of moving charge particles with different signs like Q1, Q2, and they have different concentrations like N1, N2, and they are moving with different drift velocities Vd1, Vd2. The example is the current flowing in an ionic solution, for example in sodium chloride. The current can be derived by both positive ions and negative ions, chlorine ions. So the total current would be the current due to each particle and each charge particle, and the current density will be the total of both current densities. So we will calculate for both type of charged particles and then add them. So now let's do one sample problem to revise all these calculations and the concept which we discussed today about current and drift velocity and current density.